So continuing on thematically, Jim Propp talking to us about piecewise-linear and birational modeling. It's not a word I often see in a talk title. Thank you.
Thank you. So I want to thank the organizers for putting together such a wonderful conference. I want to especially thank Tom Roby for helping to prepare this talk. Here's a word you've almost probably never seen me talk before, very few, because Tom Roby and I made it up here. But that's one of the main concepts. Also toggling, row motion, pro motion, reciprocity, which is a special meaning in our context. And all these concepts apply to dynamical systems in three different realms. The most familiar is the combinatorial realm. There's the continuous piecewise linear realm, and finally the birational realm. And you'll see examples of dynamical systems in all three of these realms. Any questions so far? Any mistakes in the slides so far? And does anyone have a really long stick that I can use? Because laser pointers have such a tiny little dot, it's hard to see with a stick. Sort of whap the screen, wakes people up. Or an empty mailing tube? Okay, I'll make do with the laser pointer. So let me give a couple of recent examples in the literature about homomesy, the first of which doesn't actually use the word homomesy because it was written before we made it up. This is work of Armstrong, Stump, and Thomas. They proved the conjecture of Panyashev. It's not so important that you understand what the conjecture says. The important thing is the form of the formula here. But I'll still say the words. Let W be a finite file group of rank R, and the Panyashev complement, whatever that is, interchains in the root coset of W, whatever that is. Then, for any orbit of the Panyashev map, we have this formula. So here we're taking a sum over all anti-chains in orbit O of something and dividing it by the cardinality of the orbit. So this is just the average of the cardinality of A. So here is the case R equals 3, root coset of 3. Those white circles represent the anti-chains in that coset. So here you have a one-element anti-chain, one-element anti-chain, two-element, two-element. Those arrows indicate the Panyashev complement operation. One element, two-element, two-element. And if you average the numbers 1, 1, 2, 2, 1, 1, and 2, 2, you get 3 halves, which is in fact R over 2. So if you want to know what the real meaning of this theorem is and how it's proved, check out this website. You can go to that page by just clicking on the link in the PDF version of the file, which is already on the web. And it already has one mistake in it. So if you want, if you can catch it before I get there. Here's a more recent example of Blue, Pechenik, and Saraceno. The history of this result is I was looking for homomessies all over the combinatorial literature, and one place I looked is this article by Stryker and Williams. And here's an example of a pro-motion orbit acting on a standard Young tableau fitting inside a 2 by 3 rectangle. And just playing around, I said, what happens if you add the two elements in the center column? So 2 plus 5 is 7. The next element in the orbit of size 3 is 2 plus 4 is 6. 3 plus 5 is 8. So the average over that orbit is 7. Here's the other orbit inside the 2 by 3 standard Young tableau acting on by promotion. 3 plus 4 is 7. 2 plus 5 is 7. The average over that orbit is also 7. Well, this one example doesn't prove anything. You do more examples like this, and you see something is going on. And what Bloom et al. Proved is that if you look at the set of semi-standard Young tableau, so more general, fitting inside an m by n box with all entries bounded by k, and will denote an element of the set of semi-standard Young tableau of that type by little t. And let's let A and B be boxes in the diagram related by a 180-degree rotation. So it could be this element, this box, and this box, or in the case of an odd by odd rectangle, it could be the center box and itself. That's allowed. And let's define capital F of a tableau little t to be the sum of the entries of the tableau that are in those two boxes, which might be the same box. Then I claim that this numerical quantity associated with these kinds of combinatorial objects has the same average in each orbit under promotion. And here's where you can find out more about that. Any questions so far? So what's common to these two stories is a setup involving three actors. A set X of combinatorial objects, an operation T carrying x to itself, some power of which, let's say the nth power, is the identity map on the set x, and a function, some numerical statistic, from x to a field of characteristic 0. Given those three things, x, t, and f, we'll say that f is homomessic, meaning same middle, same average, under the action of t, or that the triple xtf exhibits homomessy, if for all little x in the space that you're acting on, you look at the average of the statistic capital F over that orbit, that's some constant c that doesn't depend on which orbit you're looking at. So this is clearly an orbit average in the case where your orbit is of size n. In the case where your orbit isn't of size n, it's going to divide n. And this is just going to overcount every element of the orbit by the same factor. And when we divide by n, that compensates for the overcounting. So this is still an average of the quantity f over the elements x, comma, t of x, comma, t squared of x, etc., until you come back to where you started. So there are a lot of examples of this. Examples involving partitions, examples involving tableau, colorings of graphs, independent sets and graphs. There's an example involving ASMs. There's an example involving ASMs. So this stuff is all over the place, and I urge you all to look for it now that you know that there are examples like this. I want to give you some of the underlying philosophy of homomessy before I give you the main example, which will be for order ideals, cosets. Given a vector space V of functions from x to k, if you look at the ones that are homomessic, they form a subspace. So let's let V sub h be the linear subspace of homomessic functions, and let's let V sub r be the linear subspace of invariant functions, where we say a function f from x to k is invariant if f of t of x equals f of x for all x in the set. If the function is constant over every orbit, that's the same as being invariant, and if the average within each orbit is the same as the average within each other orbit, well, then the function must just take the constant value c on every orbit, so that's easy. Equivalently, if we define V sub h superscript 0 as the subspace of zero-messic functions, that is, the average over every orbit is 0, then the intersection of that subspace with the space of invariant functions is just the zero function. Now the nice thing is that in some cases, the original space of functions you were looking at can be written as the direct sum of the homomessic functions with average 0 and the invariant functions. And you can see a couple of examples of this in the most recent version of the article by Propp and Roby. But even when this doesn't happen, we find that the dimension of V sub h, the space of homomessies, has unusually high dimension, surprisingly high dimension, for naturally occurring sets x, actions t, and vector spaces V capturing interesting statistical properties of, I say statistical in the sense of permutation statistics, not probability and statistics. So any questions so far? Okay. So let's now switch to a specific example. Let P be a poset. Let X be the set of order reversing maps from the poset to the two element sets 0 and 1, which you can identify with a set of order ideals of the poset. Just look at the pre-image of the number 1, and that will be some downset or order ideal of the poset. And let's look at the most natural vector space associated with these order ideals. Let's look at the space of functions expressible as linear combinations of indicator functions associated with elements in the poset. So we'll define for each x in the poset P, 1 sub x will be an operation on order ideals where 1 sub x of I is 1 if x belongs to I, and 0 if x doesn't belong to I. And the space spanned by those functions is just all the functions capital F acting on these 0, 1 valued functions, order reversing functions little f, from the poset to the two elements at 0, 1, that are expressible in this form. You take the value of the order reversing function f at a poset element x multiplied by a coefficient a sub x, and sum over all x in the poset with fixed coefficients a sub x. If that's not quite fitting inside your brain, I'm not actually going to need that. Let's focus on the case where all elements a sub x are equal to 1. So if we take a sub x equal to 1, and we're summing f of x over all x belonging to P, where that is two valued, taking the values 0 and 1, this is just the number of elements x for which f of x equals 1, and that's just the cardinality of the order ideal. So we're just talking about things like the cardinality of the order ideal belonging to a vector space capital V. Now we need to define some dynamics on the set of order ideals. Given an order ideal I and j of p, and an element x of the poset p, define tau sub x of I, or I toggled at x, to be, wherever possible, the symmetric difference of I with a singleton set containing x. What does wherever possible means? Well, we want tau sub x of I to be an order ideal. Well, if the symmetric difference of I and the singleton set x isn't an order ideal, that would be an illegal thing to do. But if you can do that, if this thing is an order ideal, that's what tau sub x of I should be. So if the element x can be removed from the order ideal, and it was there before, take it away. If it wasn't there, but you can add it in, do that. But otherwise, just leave it alone. Okay? So this is an involution on the set of order ideals. Do it twice, you get back to what you started with. So dynamically, it is not that interesting, but we're going to use it as a building block for building an interesting map on the set of order ideals. It's worth noting that tau sub x and tau sub y commute unless x covers y or x is covered by y in the poset. So now we're going to define an interesting dynamical map on the poset, and I'm going to focus on the product of two chains, size A and size B. Extensions of other posets are in progress. And when A equals B equals 2, which will be our running example, we'll label the four elements of the poset as north, M, south, S, E, E, and west, W in the Hasse diagram in the obvious way. So now following Stryker-Williams, we'll define rho of I to be the result of successively toggling of all the elements of P from top to bottom. This is well defined because of the commutativity property. This is an operation that's been invented many times in the combinatorial literature. I won't mention all the people, but if you look at the written version of this talk, you'll see I attempt to cite everybody. If you know of people who should be cited whom I haven't cited in the paper, please let me know. So let's look at an example of row motion on 2 cross 2. So we'll start with this order ideal. Black means it's in, white means it's out. Let's try and toggle at the north element. Can we add that to the order ideal? You tell me.
No.
No, because this isn't there. So when we apply toggling at the north element, it's a no, nothing happens. Now we want to toggle in the next row. Doesn't matter which one we do next because these guys commute. Neither one covers the other. Let's do tau west. Can we toggle, can we remove this thing from the order ideal? Yes, you can. So we do that. So this is the result of applying tau W to that. Now we have to toggle at the east. It's not in there. Can we add it in? Say it.
Yes.
You should get to talk a little bit. So we add it in. And finally, we want to toggle at the south. It's in the order ideal. Can we remove it?
No.
No, because this is there. So we have to leave things alone. So this operation going from here to here is row motion applied to this order ideal. And if you apply row motion again to this order ideal, you can check, or you can just use symmetry to say that it's got to become. So that's an orbit of size 2 for row motion. So here's a theorem, first proved, I believe, by van der Vlas. A row motion on the product of two chains of length A and B is of order A plus B. Let's look at that in the case of 2 cross 2. Here's that orbit of size 2 that I mentioned before. There's also an orbit of size 4. That's what it looks like. This maps to that, maps to that, maps to that. We have an orbit of size 4 and an orbit of size 2, and both orbits have size dividing A plus B, which is 2 plus 2, which is 4. So that verifies in the special case van der Vlas's theorem. Any questions so far? Okay. We also have a homomessy result for order ideals. Here's a theorem proved by Propp and Roby. F of I, defined as the specific statistic, the cardinality of the order ideal I, is homomessic under row motion with average C equals AB over 2 in each orbit. Anyone see the typo on this slide, by the way? It's a copy and paste over. Yeah, that should be I. Okay. So for any orbit O under row motion, if we take the average cardinality of the order ideals you see along that orbit, you get AB over 2 regardless of which orbit you're in. So let's look at that in 2 cross 2. Here are those 4 order ideals with cardinality 0, 1, 3, and 4. Here's our orbit of size 2, both have cardinality 2. And the average of 0, 1, 3, and 4 is equal to AB over 2, as is the average of 2 and 2. And this holds more generally. So Propp and Roby found other homomessies for row motion on product of two chains. Einstein, that's David Einstein sitting in the front row. Tom Roby is, where's your row? That's Tom Roby. So Einstein showed that our list is complete, so we determined B sub h for this case. As a side note, row motion can also be defined for anti-chains in the Armstrong-Stomp-Thomas paper. It's called the Panushev complement. In a sense, it's not anything different from what we call row motion, but the objects it's acting on are different. And this means you have a different vector space, because the bijection between order ideals and anti-chains isn't linear. It's not going to give a linear map between the associated spaces that are combinations of indicator functions. So the homomorphic story is quite different in the two cases. So keep in mind that just because there's a bijection doesn't mean you get the same homomorphic story. But now I want to take us from the bottom realm, the combinatorial realm, to the middle realm, the piecewise-linear realm, the order polytope. Sorry, there. So the set of order ideals is naturally identified with a set of order reversing maps to the two-element set. Or we could just as well have defined everything in terms of filters. We could define toggling to the set of order preserving maps from P to 0, 1. But now let's interpolate. Turns out there's a natural way to lift toggling from the set of order preserving maps from P to the two-element set containing 0 and 1 to the set of order preserving maps, that period should be comma. Order preserving maps from P. Can you take note of typos on the slides so that later? Gotcha. Order preserving maps to the interval from 0 to 1. And the set of such maps, viewed as a subset of reals to the power of the cardinality of the poset P under some indexing of the elements of the poset, is Stanley's order polytope, whose vertices correspond to the order ideals of P. It's usually handy to augment the poset P by adding a bottom element 0 hat and a top element 1 hat, even if your original poset already had a minimum element and a maximum element. And we'll define, we say that x is, every element x of the original poset should be strictly larger than 0 hat and strictly less than 1 hat. And the order polytope can be thought of as the set of vectors associated with functions, f hat, taking p hat to r, that satisfy f hat of 0 hat equals 0, and f hat of 1 hat equals 1, and are order preserving. So let's see that in 2 cross 2. So we map 0 hat to 0, 1 hat to 1, and everything in between is weakly increasing as we go on. Any questions so far? We can toggle in the order polytope. For each x in P, define toggling in the order polytope at x to be the map that sends some order-preserving function f from the poset to 0, 1 to the unique f prime, such that, here the hats mean include the 0 hat and 1 hat in the picture. F prime hat evaluated at y should be the same as f hat of y, as long as y is not equal to x. So we're not changing any of the numbers except at x. And the number at x, we're changing according to this formula. You take f hat of z for all the covering x, take the minimum of those. Add to that the maximum of f hat of w over all w's covered by x, and then subtract f hat at x itself in the case of y equals x. So this is an involution. It's also a continuous piecewise-linear map from the polytope to itself. And this definition is implicit in the work of Kirillov and Berenstein. Propp also mentions it. If you know more about the history of this and more people I should acknowledge, please let me know. Here's what that looks like in a concrete case. Here's an element x of the poset. It covers W1 and W2. It's covered by a Z1 and Z2. Let's say that f of x is 0.4, and f of Z1 and Z2 are 0.7 and 0.8, and so forth, as shown in this figure. And we want to toggle at x. How do we do that? Well, we look at the value of the function at the two values below here, 0.1 and 0.2. We take the maximum of those. So the maximum of those is 0.2. We look at all the things above it, 0.7 and 0.8. The minimum of those two circles is 0.7. So that means that 0.4 has to lie, the number that we replace x by, notice the 0.4 lies between 0.2 and 0.7, which they better do because it's in the order polytope. So if we're going to replace this by some other number, it has to be some other number in the interval between 0.2 and 0.7. So replace it by the opposite number in that interval, where opposite just means exchange the endpoints and apply the affine map, the unique one that switches the two endpoints of the interval from 0.2 to 0.7. And it's easy to show that another prescription for that is take the values of 0.2 and 0.7, take the endpoints, and subtract from their sum the old value. So 0.4 plus 0.5, that's the new value, equals 0.2 plus 0.7. And there we see that down there. Questions so far? So now that we've defined what it means to toggle in this realm, we can define row motion in the order polytope in analogy with row motion acting on order ideals as a result of forming CPL toggling at the vertices of P from top to bottom. And our original combinatorial row motion is just CPL row motion restricted to the vertices of the order polytope. So here's an example of CPL row motion. Here I've left out 0 hat and 1 hat in the picture. So here are the values at the vertices of 2 cross 2. You toggle the 0.8, that becomes 0.6. For reasons of time, I'm not going to walk you through all the steps here, but this is what it looks like. You toggle it north, west, east, and south, and you get this element of the order polytope. I want to give a quick aside on promotion if there's time. Let me see how I'm doing. 10:21.
You have to go over there.
Oh, okay. So, because time is short, let me just say that there's another operation called promotion, and it deserves the name because you can relate Schützenberger promotion on semi-centered Young tableau of rectangular shape to the action of this operation on lattice points and the dilation of this polytope. So you take the order ideal, you take the order polytope, you can act on a dilation in the obvious way, and that has something to do with Schützenberger promotion. But let me move on from there. Einstein and Propp showed that this operation is of order A plus B, but periodicity in the CPL setting, we have not been able to derive from periodicity in the combinatorial setting. Even though the combinatorial setting is the vertices of the order polytope, we can't seem to get our argument to work. So we'd like to know a self-contained proof of periodicity for CPL row motion. We've also classified the homomesses of CPL row motion, and they're the same as the homomesses for combinatorial row motion. For instance, setting all coefficients equal to 1, if you just take f of x, so take your order-preserving function from the poset to the real interval from 0 to 1, add up the values for all x in the poset, that's homomessic. The average under row motion orbit is the same regardless of the orbit you're in. Now the way we prove periodicity for CPL row motion is by deriving it from the result in the third realm, the upper realm, the birational realm. So a birational map from Cn to itself is a rational map which has a rational inverse. And by inverse I mean, well, yeah, it need not be defined everywhere because rational functions like x goes to 1 over x, have singular behavior in some places. But off of a proper subvariety, it should have something that undoes it. To lift toggling to the birational setting, you replace plus, minus, max, and min by times divided by plus and parallel plus, where the parallel sum of x and y is the reciprocal of the sum of the reciprocals of x and y. So letting sigma plus and sigma parallel denote the ordinary sum and parallel sum, we can define birational toggling in a way completely analogous to the way we define piecewise-linear toggling. So I'm going to rush a bit. Defined birational row motion as doing birational toggling from top to bottom. Grinberg and Roby showed that birational row motion on A cross B is of order A plus B. And it's not hard to show that the homomesses for CPL row motion lift the homomesses for birational row motion. For instance, take a function f, evaluated at the elements of the poset x, take the absolute value, take the logarithm now, and sum over all x. That's a homomessic function. So here's the picture. You have facts in the birational realm, which can use to derive facts in the CPL realm, and use them to derive facts in the combinatorial realm, and to some extent inspiration can go from bottom to top. Look for analogs and things up there. But the hardest part, from my point of view, of this whole setup is this reciprocity lemma. Grinberg and Roby proved the periodicity theorem and the reciprocity lemma separately. You can really derive the first and the second. Reciprocity says that if you have some element x in the product of two chains, x equals ij, then g of y equals 1 over f of x, where y is another element of the poset. It's related to x by 180-degree rotation, and g is a certain power of row motion. Here it's birational row motion. There's another typo. So the period reciprocity lemma, like you bet, ignore that. So here's what reciprocity looks like. Here's an orbit of row motion in 2 cross 2 in the birational realm. This z corresponds to the 1 over z there. This x corresponds to the 1 over x there. This y corresponds to 1 over y there. And and this W corresponds to 1 over W there. Question. Is there a self-contained combinatorial proof of the fact you get when you take that birational reciprocity result and bring it down to the lower realm, to the combinatorial realm? Combinatorial reciprocity, well, let me just show the example, so I'm out of time. Here's an orbit of size 4. It's actually an orbit of size 2, twice. So the claim is that here, if you look at the left panel, just look over there, you'll see I'm looking at all the different elements of the poset. And then I'm looking at other elements of the poset for these other places in the orbit. And there's a systematic way of saying which thing I'm circling. And it's always the opposite element of the poset, and exactly one of them is in the order ideal, and exactly one of them is not in the order ideal. So I'd really like to know a combinatorial proof of this. Question I hear a lot is, does all this homomessy stuff have anything to do with cyclic sieving? Answer, not much, except they often occur together. Roby's grad student Mike Joseph, raise your hand, Mike. There. Is studying a family of combinatorial systems, one of which, for instance, the set on which it's acting has 377 elements, but the LCM of the orbit sizes is over 3 million, so the smallest cyclic group that can reflect that orbit structure is a cyclic action of order over 3 million, much, much larger than the set, so it doesn't really look like cyclics. Question I'd like to hear is, how can I find out more? Glad you asked. See the posters of Dowie Grinberg and Tom Roby, and also Nathan Williams later today. See slides for 1-hour talks by myself and Tom Roby. Read the exhibit abstract for this talk. Hassle/encourage me and Roby to finish the Propp-Roby article, and Einstein and me to finish the Einstein-Propp article. Read Grinberg and Roby's long, but hopefully soon, maybe not so long, paper on the archive, and attend the AIM meeting on dynamical algebraic combinatorics in 2015. Thank you for listening.
Questions?
So you have a periodic piecewise linear automorphism of the order polynode. So what do the domains of linearity look like?
They're not what you originally think they are, because when you iterate the map, the original pieces get chopped up into smaller pieces.
Right.
But that's a very good question. It would be very nice to have some decomposition of the order polytope into pieces, each of which has linearity of the map and all its powers. Yeah. Good question. Yeah.
I was curious if the toggling maps of fixed points in the order polytope, what can you say about, I guess, functions on a poset where where toggling anything does nothing. Toggling any element. So each element is there. For each x in the poset, f of x is exactly the average of what it's allowed to be.
Okay, there are examples of that. I can't remember if there are for these specific classes.
The piecewise linear, if you have,
Oh, yeah.
they're
If it's-
equal.
Yes, that's right. So in the piecewise linear case, if you just have a function that's a linear function of rank, increasing from bottom to top, that will be fixed.
Right, but who said it was ranked?
But if it's not a ranked poset,
Yeah.
most of these things don't work as well for non-ranked posets.
Okay.
I don't know much about non-ranked posets.
Okay.
Time for one more.
So all of this is looking at, you would think of it looking at averages. What higher moments? Any
Higher what?
higher moments?
Higher moments.
Deviation?
I have not been able to find much along those lines, but I would love to.
But you've looked.
There are some cases of that for, I mean, this is sort of related to rotor routing. It kind of grew out of rotor routing. For rotor routing, there are cases where things generate second moments, not just averages, but it seems to be kind of different, so I haven't been